of PKC 2022. So we'll be having 6 presenters in total, and maybe 7. And the first one is lattice-based signatures with tight adaptive corruptions and more. The authors are Jiaxin Pan and Benedict Wagner. And I think Benedict will be giving the talk. You can start anytime.
Yeah. So can you see my slides now? Yeah.
Yep.
Okay. Yeah. Thanks for the introduction. I'm Benedict, and this is a joint work with Jiaxin Pan. And this is on a high level about tightly secure signatures in the multi-user setting from lattice-based assumptions. Okay. So when we typically think about digital signatures and formalize their security, we have a picture like this in mind, where one user has a secret key and all the other users know the corresponding public key, and also the adversary knows the public key and tries to forge some signatures. And this is captured in the standard UFCMA security game, where we send a public key to the adversary, and the adversary can ask for signatures, and in the end it outputs a forgery. And it wins this game if this is a fresh forgery and a valid message signature pair. Okay, so this is standard and well known, but if we look at it, then we see this is not really what's happening in practice, right? Because in practice, you have a lot of different users, and all of them have their secret keys and public keys and share the same system parameters, and they communicate with each other. And an adversary can be an outsider that observes the system, or it can also be an insider that corrupts some of these users and learns their secret keys. So let's try to model this as a security game. So first, we give n public keys to the adversary, where n is the number of users in the system. Then the adversary can again ask for digital signatures for messages of its choice. And now he also specifies which user should sign these messages. And then the adversary can also ask for secret keys. So this corresponds to the corruptions that I told you about. And in the end, it outputs forgery I star M star sigma star. And now it wins if this is a fresh message. So it has never been signed. The user is not corrupted. So he never learned a secret key. And this is a valid message signature pair for that user. Okay, so this is a slightly more realistic notion. So let's compare these two notions. So we have the single user security on the left and the multi-user security on the right. So it's relatively easy to see that you can just take this public key and embed it in a random public key on the right. And then you will show that asymptotically, the single user security notion implies the multi-user notion. And this is a guessing argument, and it comes with a security loss of n. So it's proportional to the number of users in the system. And this is bad if you want to choose your parameters in a theoretically sound way according to your security proof. Because let's say you have 2 to the 30 users in the system, then you lose 30 bits of security, and this will result in inefficient parameters. So if we want to avoid this, we need a tight reduction. We say a reduction is tight if such a security loss that we have is a small constant and independent of what the adversary does. So let's look at the state of the art for tightly secure signatures. We can look at the classical assumption setting and the post-quantum assumption setting. And in the classical and post-quantum assumption setting, we already have tightly secure schemes in the single user setting. But as I showed you, this is not what we are interested in. And in the multi-user setting, we only have reasonably efficient schemes from classical assumptions. And our work closes this gap on the right here. So our goal was to design a signature scheme with tight multi-user security from post-quantum assumptions, such as lattice-based assumptions. And we also want to have some compactness guarantee. So for example, for lattices, we want that our signature only contains a constant number of lattice vectors. Okay, so let me just briefly sketch why this is not trivial. So the problem is that if you want to have a tight reduction, then your reduction should know all the secret keys, because it has to answer all the corruption queries. And if you know all the secret keys, then you can just forge without using the adversary, and therefore your underlying problem cannot be hard. So this is the high high-level problem that we have to solve. We solve it using non-unique secret keys, essentially. So we give a generic framework that transforms dual mode commitment scheme into a signature scheme that we want using sequential OR proofs. And this is actually a generalization of last year's PKC work by Diemet et al. And it allows us to instantiate it from post-quantum assumptions such as LWE and a group action-based assumption. So as we use sequential OR proofs, we also thought, well, can you do the same thing with parallel OR proofs? And we show that you cannot do it. So this is a gap between sequential and parallel OR proofs. Okay, so let me conclude with some open problems. So what we show is a tightly secure signature scheme in the multi-user setting from plain LWE. So what about different assumptions? So let's say you want a search assumption SIS, or you want to have structured lattice assumptions. This will give you a more efficient scheme, but our approach does not work for these assumptions. And also our approach is in the random oracle model. So typically you would desire a quantum random oracle model or a standard model. So yeah, that's it from my side. So if you're interested in this work, you can look in the paper, which is on ePrint, or also at the long presentation, which gives you more details. Okay, yeah, thank you.
Thank you for the talk. Are there any questions? So people can ask questions either on chat, raise their hands, or on Zulip. So far, I don't see any questions. So maybe I could start off the question. Then I guess one of the simpler question is, why is your solution limited to structure lattices? Like, what's the barrier there?
Oh, okay. So it's actually the other way around. So we cannot achieve it from structured assumptions, and we can achieve it from plain LWE. So the thing is that what we have to construct on the way is a lossy identification scheme with some multi-key indistinguishability in a tight way. And we know how to do a lossy identification scheme from structured assumptions, but we don't know how to do it in a tight way for many keys at the same time, right? Because you have many users, you need to have this lossy identification scheme for many keys. And our technical contribution is maybe the main technical contribution is to have this lossy identification scheme from plain LWE in a tight multi-key way. So it's the first lossy identification from plain LWE that we construct. And the problem is that we cannot do it from ring LWE. So in the single user setting, you can construct a lossy ID, but in the multi-user setting, it's not clear how to do it in a tight way.
I see. Okay, thank you. Are there any other questions? Because if not, I did have one other question, and that was you said your scheme achieves compact signature with constant elements in the vector. Like, did you actually put some concrete numbers on that, or is it asymptotic right now?
No, yeah, so this is a limitation of our result. It's basically only an asymptotic efficiency improvement. So I mean, this is related to your first question, right? So if you compare concrete numbers with let's say dilithium or other optimized schemes, it's not clear that our scheme will be more efficient, but it's the first step on the way of having this. And of course, the most desirable of these open problems is to transfer it to a optimized ring setting, and then you could compare it with the other schemes. So we don't have any concrete sizes in bytes or something like that.
Okay, great. Thank you for the talk. If there are no other questions, maybe we could move on to the next speaker. So the next talk is Count Me In Extendability for Threshold Ring Signatures, and the authors are Diego Arana, Anca Niculescu, Matthias Hall Anderson, Elena Pagnin, Sofia Yakubov. and Elena will be giving the talk.
Yes, thank you for the introduction. Let's see. Is this working?
Yes, it is.
Perfect. Okay, so here we are presenting this wonderful work. What's this work about? Well, I guess everybody now is aware about digital signature schemes. We have set up key generation, signing, and verifying. And for the purpose of this talk, I will represent public keys with these circles here. In the standard case, we have one message and one signature. And the signature is connected to just one public key. Then we have ring signatures, which have essentially the same kind of algorithms, but the signing algorithm takes an input, a ring of n potentials public key, and we only know that one of these keys has signed the message, but I don't know who has signed this message. And an extension of this, and these are used, for instance, in Bitcoin or in whistleblowing cases to show, okay, there is one person in this institution or among these people that is endorsing a message. An extension of ring signatures is threshold ring signatures, where instead of having just one potential signer, we have T potential signer inside this ring of n signers. And what we do in this work is create yet another extension of this, because, well, there are a couple of drawbacks with the existing signatures, threshold ring signature schemes. The first one is that they require interaction among signers, or if they don't require interaction among signers, then there needs to be an agreement, at least among the signers, on which ring of public key to use. So implicitly, there must be some interaction, and we don't like that. So the way to avoid it is basically by constructing an extendable threshold ring signature scheme, which would be useful in contexts such as me too, count me in, I endorse this, I joined the Kickstarter afterwards. Intuitively, I have like T out of n signers from a threshold ring signature scheme, and I want to be able to extend this signature to a number T out of n prime signers. So I want to extend my anonymity set, and then potentially join a clause that someone else has started by increasing the threshold size by 1. So this is the overall idea of what we create. And what we achieve is that we can have a dynamic way in which the ring can grow, and there is no need of interaction among signers. So we are happy. So to summarize our contributions, we have extendability, which means largely the set of potential signer of a given signature. And we do this not just for threshold ring signatures, which is the main selling point, but also for same message linkable ring signatures and the standard ring signatures. We, of course, introduce syntax and security models, and we have basically as many construction as authors and the implementation of the most efficient constructions. Concretely, we present way to construct a extendable ring signature from signature of knowledge in a black box way, and then compiler generic transformation from same message linkable extendable ring signature. We can generate extendable ring signature using an additional assumption, which is signature of knowledge. And then we can build the extendable threshold ring signature, again, in a black box way from same message linkable extendable ring signature and the discrete log assumption. Two different constructions. I guess that's my quick summary. I want to go to bed. Good questions.
Thank you for the talk. We have quite a few time to receive questions.
Good.
So if anybody has any, let us know. In the meanwhile, I guess I have, this is a naive question, but can you bring up the first slide that you had?
The first slide, yes.
Or maybe the second one after
maybe the second one, I guess. Yeah, I guess you want the end of this.
Yeah, end of it, yeah.
So, yeah, something like here. Getting there.
Oh, yeah, this sounds like a really interesting extension to these standard ring signatures. And one question was, when you use this like extend function on standard ring signatures, what's the difference between just signing with this new n prime ring? Like, it's more efficient?
Yeah.
Or?
Yeah, well, if I sign, so first of all, there needs to be not exactly an interaction, but I need to see, let's say, your ring signature. And then I cannot just join that ring signature. I cannot add my secret key to endorse it. The extension, on the other hand, would require the signer to sign for a bigger ring. So it cannot be done publicly with existing constructions.
Right. Okay. So when you
The extension is done publicly. I'm just throwing in more potential signers, but because I don't have their secret keys, they're just, augmenting the anonymity set. It's only with the join that I place in my secret key.
I see. So, when you have a ring signature, and you mentioned that you, okay, yeah, right. I understand now.
Yeah.
When you
but good point. Like, because it looks like, oh, come on, I can always throw in public things. Like, no,
Right.
not with the ring signature, because like you're then basically forging, because then you're changing what the original signer signed.
Right.
So we need a new security model to handle this, and we need a different notion of anonymity according to how you extend the join, extend, how you play with these two operations.
When you run this extend and join algorithm, do you need any public key information, or is it just a message and the signature?
So for the extend, it's a message, initial signature, and the public keys that you want to include.
Mm-hmm.
And for the join, you need your secret key and the existing message and the existing signature, and then you will create a new signature.
So you don't need the previous ring member's public key to invoke the.
Well, that's kind of included in the signature because it's an information that you need to have in order to verify. So it's yeah.
Okay.
But in some of our construction, you wouldn't need to read those keys. You can just perform an operation without reading all of the other public keys.
Okay, I see. So there's one question on chat. Maybe I can read it. It's from Chalisa, and I missed the first part of the talk, so might have missed it. But wait, but do extended signatures look the same as non-extended signatures, or does this become a privacy leak over time?
That's if they provide anonymous extendability. So we model this notion of anonymous extendability, so you cannot track, let's call ladder, the sequence of extend and join and extend that you do. You cannot distinguish how you have performed these operations. So if the signature scheme satisfies the stronger notions, then you cannot distinguish a fresh signature of a big ring from one that has been extended.
Okay. Yep, that answered the question. So we have a few more minutes left, but I guess one last one that I just wanted to recap on. So what kind of assumptions can you use to build this new primitive?
Yeah. Okay, so we can build them from extendable threshold ring signature, discrete log, and public key encryption. We can build them in a black box way from same message linkable extendable ring signature and signature of knowledge. So basically signature of knowledge is the smallest one. And then from that, you can build up adding simple things like public key encryption and delog. We also have a construction on group on unknown order, but we didn't include it in the paper. So maybe we'll pop up in a few months.
Okay, like in the journal version, maybe.
Yeah. Good.
So I think, yeah, we can move on to the next talk then.
Yeah, for any more questions, just drop me an email. I'm happy to reply when I'm awake. See you.
Right. So the next talk the title is A Note on the Post-Quantum Security of Ring Signatures. And the authors are Rohit Chatterjee, Kaimin Chung, Jiao Liang, and Giulio Malvolta. And wait, who is going to be giving the talk?
Me, Rohit, sorry.
Oh, sorry, yeah, Rohit, go ahead.
Sure. 1 second. Can you see my screen?
Yes.
All right, let's roll. Hi, I'm going to be talking about the post-quantum security of signatures and ring signatures. This is joint work with Kaimin Chung, Jiao Liang, Giulio Malvolta. We'll start with the post-quantum security of standard signatures. And standard signatures usually means unforgeability. So let's start with classical unforgeability. You have an adversary talking to a challenger that gives it a signing oracle, meaning it receives signatures on messages of its choice. And eventually it produces a forgery on the particular challenge message. And this definition works as long as the challenge message is not queried beforehand. If the adversary is a quantum machine, however, and can make quantum signing queries, then this changes because the challenger also has to put out states over signatures. And it quickly becomes clear that we cannot define query messages cleanly because the adversary's queries can be superpositions over the entire message space, which means that we cannot cleanly define what messages are not seen by the adversary. And so unforgeability also becomes tricky to define. So we have to look at other more nuanced definitions in this quantum setting, and the definition we look at is called blind unforgeability. It was introduced in the work of Alaik and others in 2020. And this has the adversary, again, talking to the signing oracle over some message space. And what happens here is the adversary submits superpositions and get back signatures just as before. But now the catch is the signing oracle has this blind set, which is of weight epsilon and chosen uniformly from messages. And it does, what it does is it does not sign messages over the blind set, meaning if the adversary has a certain superposition that includes members in the blind set, then the oracle just simply does not return signatures over there. Eventually, the adversary has to put out a forgery, and now we also expect that, apart from being a valid signature, the message corresponding to the forgery also comes from inside the blind set. And it's also easy to see that this is equivalent to standard definition classically, and people have been looking into this definition recently. And with this definition in mind, we can look at our results, which is first, we show that a scheme based on quantum PRFs and the quantum hardness of SIS is blind and forgeable in the QROM. We also give another scheme that is based on the same assumptions and is blind and forgeable in the plane model. And both these schemes are compact. We also develop a meaningful extension of this definition to the ring signature setting and give a new definition for ring signatures in the quantum case. And of course, we also give a construction of ring signatures satisfying our new definition in the plane model. We'll very briefly look at our plane signature scheme. And this proceeds as follows. This follows a paradigm that has been widely used to design IBE schemes and signature schemes from lattice-based assumptions. And we have a wide matrix BM corresponding to each message M. And the signer has an SIS trapdoor TA for the left part of this matrix. And that allows it to generate signatures, which are basically elements in the right null space of BM. So these are essentially SIS solutions of some kind. And F here is a special PRF that we use, which we call epsilon biased bit PRFs. And with these ingredients, we can show that this is blind and forgeable in the plane model. And this signature is also compact. Now we'll turn to the ring signature case. As we just saw, ring signatures are these signatures where you have a group of people and any member in the ring can sign on behalf of all the members without any prior interaction. And the properties we expect are unforgeability, just like normal signatures, and anonymity, meaning that any other entity apart from the signer cannot tell who actually signed a given message. And since we look crucially at unforgeability, we will recap a classical ring unforgeability, which proceeds as follows. There's a challenger and an adversary. The challenger first produces a universe of Q public and private keys and gives out the public keys to the adversary. The adversary can now produce signing queries with messages and rings of its choice and get back the corresponding signatures. It can also produce corruption queries where it gets back the secret key for the corresponding user. And finally, it has to output a forgery where it must be the case that the ring corresponding to this forgery does not include any corrupted members, otherwise signing would of course be trivial. Our modification to the quantum setting consists of the following steps. So we have the same setup as before, and the challenger again produces a universe of keys. But now, of course, the adversary's signing queries can be of quantum form. And here, this means that we sign over superpositions of both messages and rings, and the challenger responds with the correct superpositions of signatures. Since we follow the blind unforgeability definition, the signing oracle is blinded, just like we saw before. And the blind set is over both messages and rings for compatibility. The corruption queries are produced the same way as before. They're kept classical because there's no meaningful intuition for corrupting, let's say, a superposition of parties. Eventually, the adversary has to produce a forgery, and now the requirement for this to be valid is that the message and the ring belongs to the blind set we described before. So this is our new definition, and that brings me to the end of my talk. Thank you for your attention, and please see our longer talk and full paper. Thank you.
Thank you, Rohit. So we will take questions now. If there are any questions, please raise your hand or ask them on Zoom or Zoom. Can I ask one like a very simple question? So this was my first time hearing about this this notion of blinded unforgeability. Can you kind of like show the slides and explain a bit more
Sure.
about that?
Let me share once again.
I guess one of the things that I was wondering is this blinded set, who chooses it? Is it the adversary or is it the challenger or?
The challenger picks the blind set, so there's some amount of selectivity. So, but the parameter epsilon can be considered to be adversarially defined.
I see. So when I think you mentioned that this includes the standard notion of unforgeability. Does it capture like adaptive unforgeability too, or is it the selective setting?
No, yeah, it captures a classical standard unforgeability. Yeah, adaptive.
Okay.
Yeah.
I see. Also, if there is no other question, I have one more. And so are there any, like, let's say, contrived scheme which satisfies classical standard unforgeability with against quantum adversaries, but fail to provide blind unforgeability?
Right. I think, yeah, so the work that introduces this definition has a scheme of that kind, I think.
Okay. Sorry.
But of course, it's one of those tricky quantum things. It's nothing immediately natural.
Okay, thank you. Sorry, so there are several questions on chat now. So one of them is by Rune. What is the density epsilon of the blind set?
Well, the definition is parameterized, which means that you allow any possible value. What this means in practice is it can be any inverse polynomial thing, and you can consider it adversary specified. That's your total definition. Just the game itself is parameterized with epsilon. You can use any value.
And I guess you mentioned that the epsilon can be is adversarially chosen.
Yes, yes. So you can consider pairs of adversaries and the corresponding epsilon. That works best for you.
Okay, so I think that answers all the questions on the Zoom chat right now.
And Abida also had her hand up.
I raised my hand. So I'll go ahead. So I was just wondering, when you have the game defined and you said that the challenger gives the universe of keys
Sure.
to the adversary, is there a reason that like the universe of keys has to be set at the beginning of time?
No, it's just the standard ring signature unforgeability definition, and we follow it. There's no particular intention behind that. Of course, it does make things easier in the quantum case, because when you specify these keys, you do not have to describe quantum access to them, which might become a problem. It doesn't, because yeah, we keep it classical there.
I've been told that Jacob, you were raising your hand too. Sorry, I don't know where to see this hand in.
Yes, no, I mean, I actually lowered my hand again, but my question was sort of related to the previous question regarding this setup for the keys, because I mean, even in the classical setting, I guess you could consider an adversary who would maliciously generate public keys and ask for ring signatures that includes these maliciously generated keys.
Oh yes, that is allowed. Sorry to cut in. Yeah.
So my, I guess I could repeat the question. Is there a reason for why you do not consider maliciously generated keys, or can your result be extended to the setting where you would have maliciously generated keys?
Yeah, maybe I didn't explain clearly, but you allow this behavior is still allowed. It's just that challenger has its own set of keys that it generates beforehand. The adversary can, of course, produce rings of its choice. Yeah, I guess this doesn't show up very clearly in this definition, but this is, of course, allowed. This ring R for signing queries can be any ring, including members of the adversary's choice.
Okay, thank you.
Yeah.
All right, thank you for the talk. I think we should move on to the next talk then.
Sure, I'll stop sharing.
Thank you. So the next talk is logarithmic size linkable threshold ring signatures in the plane model. The authors are Abida Hawk, Stefan Kren, Daniel Slemaning, and Christoph Streaks. Yep, you can start, Abida.
Abida, you're muted.
You should be able to hear me now.
Yes, we can.
Thank you. Thank you, Shu, for the introduction. So this is, yeah, well, you already said the title. Let's see, and hopefully, there we go, sorry. So we already talked about ring signatures, but let me motivate a scenario where you would want to use threshold ring signatures. I'm calling it the Parliament's problem. So let's say Charlie is really mad about British taxation without representation. So he wants to sign a petition, and he's going to say, look, we're going to throw a lot of tea into the Boston Harbor in the middle of December. Now, with signatures, I think everybody knows he can sign this message and send it off, and anyone can check, yay, this really did come from Charlie. But I mean, this is a crime, so it's a sensitive thing to sign for. So what Charlie might do is hide his identity among a set of known people, which I have here as Alice and Bob. So now when this message gets sent over, it's actually with respect to this known ring of people, and nobody can tell from whom the message actually came. Of course, this is not going to be enough if just Charlie wants to do this. We need to see if other people want to join and help him out with this crime. And that's where threshold ring signatures would come in. And Elena actually talked about this already, and she even pointed out that there seems to be a problem with threshold ring signatures, which is, well, don't the signers have to talk to each other? And she already started talking about like same message linkability. So it seems like maybe we don't. So we have kind of a related notion, which is this concept of inter-signer anonymity. The idea is pretty straightforward. We just force our ring signature to have a deterministic part. And then if a verifier is given two signatures, which are on the same message and ring, they can just check if that part is equal. If it is, they'll say, it's from the same signer. And if it's not, it's from distinct signers. So for example, if I have 5 signatures and I do 5 choose 2 checks as the verifier, and they're all different, I'd say, oh, at least I got 5 signatures from 5 different people from this ring. And the idea here is that it's more fine-grained than linkability, because not only could we do this over just 2 signatures on the same message and ring, but we can actually set the scope to be whatever we want and make it so that we can do this equality check based on whatever situation we want to have. Okay, so I obviously in 5 minutes don't have time to go over how our construction looks, but we used a ring signature template from Backus et al. And actually Rohit would be familiar with this as well, because their ring signature scheme uses something similar. And so that's how we were able to get that logarithmic size ring signature with something called the somewhere perfectly binding hashing. And then we're in the plain model because we use a non-interactive witness indistinguishable proof, or NIWI. So that's already been done. What we did that was new was getting that deterministic part, like I said, which we use a verifiable random function for. So just quickly, since I can't go into the construction, I don't know what I did. I clicked on something. Sorry. So the signature ends up looking like this proof of either I am signer I, and I have a bunch of values that are consistent with signer I's like an index I, or I'm signer J and I have a bunch of values that are consistent with that. And in particular, I have this value V here, which is the output of the VRF. So that's the value, and it's a deterministic value. And then the honest signer, if he's I, for example, he's just going to put some random stuff here for J. And then one more thing that we have is this relationship RF, which we're going to need in the proof. So I'll show you. So I think the anonymity proof is actually pretty interesting because it points out an interesting problem where basically when you want to prove that a ring signature, this ring signature is really anonymous, you have to anonymously switch or indistinguishably hop from a signature from signer I to a signature from signer J. And so when you have, when you jump and try to make all the values from signer J also be true along with signer I, it causes an issue where it's actually possible for one to distinguish real signatures from this sort of made up signature in the anonymity hybrid. So we're forced to use this like other relationship called F. And F is a one-way function, and it sets this relationship between signer I's secret key and signer J's secret key. And this would never happen in reality for real signatures, but we need it. You can think of it as like a temp variable where we use it as set it to be true so that my NUI can remain true until such time as I can make it false again because the signature is from signer J. Cool. But this leads to a problem because if there is an adversary who wants to join the ring and they wanted to do so maliciously, they could forge signatures trivially because all they would have to do is pick SKI and SKJ according to this one-way function. And then I said, okay, look, it should be linked each time you have the same message in ring, but if you use the relationship F, that's not going to be the case. So I lost the ability to have the adversary register malicious keys. It's still possible for him to like get all sign queries that he wants, or even ask for honest keys to be added to the ring. And because this is threshold, he can also corrupt keys, but still those keys are honestly generated. So this doesn't quite match like the kind of open setting that we would want for ring signatures, but it seems unavoidable because we really wanted that intersigner anonymity and we wanted to stay in the plain model. So that's it. Of course, please see our paper on ePrint or check out my longer video. And of course, with the previous presenters, I do recommend Rohit's and Elena's papers as they are quite related to mine.
Okay, thank you for the great talk. Are there any questions from the audience? So right now, I don't see any yet. Maybe I can ask a very simple question. So you mentioned that you introduced a new, more fine-grained definition for linkability. So is this something, if we didn't care, let's say, if we want a very efficient scheme based on, ROMs or whatever, is it easy to achieve this, or does it provide like new insights to construct?
So I guess the question is like, does my ring signature scheme like provide like new insights over previous linkable ring signatures?
What I meant is that I guess the previous linkable ring signature doesn't provide intersigner anonymity, right? Or does it?
So I guess maybe this is like the name is just because we wanted to make it look like more like threshold ring signatures, which if everybody was agreeing to sign a message, then it would be on the same message and ring each time because they're working together. And so our first thought was, well, let's just make it be on the same message and ring. And then it was kind of straightforward to say, well, if we like scope it so that you can only check if two signers are the same on the same message and ring, we can change the scope to be whatever we want. Like if you had an election, I could vote for the mayor. And if I then vote for the governor, nobody's going to link that those two signatures came from the same person, which is how other like previous linkable ring signatures have done it. Elena mentioned like same message linkable, which like changes the scope, but we have just, you can make the scope whatever you want equality to be checked on. I hope that answers the question.
Yeah, it did. Thank you. Are there any other questions? So if not, we are on a good time schedule right now, so maybe we can move on.
Sorry, one more question.
Oh yeah, go ahead.
Yeah, I was asking if you considered any constructions without VRFs and if you have any thoughts on that.
Without what again?
Verifiable random functions.
Without verifiable random functions. So I guess it seemed like the easiest way to just make that deterministic value work out so that we could like prove something about it. Like you actually need to use a secret key. So I'm not sure. I don't know if there's like another object that would give us that same kind of property. So I guess the answer to your question is no, but if you have a thought, I'd like to know.
Right. Yeah, no, that's a very fair answer. Thank you.
Okay, thank you, Abida. Let's move on to the next talk. The title is On Pairing Free Blind Signature Schemes in the AGM. The authors are Julia Kastner, Julian Ross, Jayu Shu, and Julia will be giving the talk.
Yes, hello. Thank you for the introduction. First, I'd like to explain the type of signature scheme we looked into. It's a 3-move blind signature scheme. This is a 2-party protocol with a signer who has a secret key and a user who knows the corresponding public key, and he has a message that he would like to have signed by the signer. And to do this, they send back and forth 3 messages. And in the end, the user can compute a signature on the message that he has. And we have 2 properties for this. One property is the blindness. So the signer, informally speaking, should not learn what the message is that he signed. And on the other hand, we want a one more unforgeability property, which means that the user cannot generate more signatures than the signer interacted with him. The first scheme we looked into in this work is blind Schnorr signatures. So in the blind Schnorr setting, on the signer side, we just have sort of a proof of knowledge of this discrete logarithm X here, which is the discrete logarithm of the public key Y. And the signer proves that he knows the discrete log by generating this R uniformly at random and sending over G to the R. And then when he gets a challenge, he computes S, which is C times X to the X plus R. So this is then sent back to the user. And on the user side, the user just first blinds these values to generate the challenge. And then later on, he unblinds them to generate a Schnorr signature on the message that he has. We know for Schnorr signatures, for blind Schnorr signatures, there's a way to break the one more unforgeability without breaking D-log, which is the Ross attack, which was discovered by Schnorr. It's basically an attack where if you have a lot of open signing sessions, you can try to linearly combine hash queries to generate a one more forgery. We also know that in the standard group model, so without the AGM or GGM, we cannot use the standard forking technique to prove that these blind Schnorr signatures are secure. But we know that in the AGM plus ROM, under the Ross assumption and one more D-log, there is a proof of security. So the Ross assumption is just that this combining hash queries should be hard. But we found out very recently, so we learned very recently that this is actually possible to do in polynomial time. So we wanted to look into a setting where these this Ross attack does not apply, which is a sequential setting. So in the sequential setting, the user needs to always close signing sessions before opening the next one. And there we can show that in the AGM plus ROM without Ross, blind Schnorr signatures are secure under one more D-log. And we also show that our reduction is optimal in the sense that it makes as many D-log queries as it needs to make, but not more. On the other hand, we considered a scheme by Abe. This scheme is based on an OR proof. So you have this green branch of the OR proof, which is just basically a Schnorr blind signature. But we also have this pink part of the OR proof, which has more structure. And so this has 2 interesting properties. One of them is that you can use either branch to generate a signature. So in the honest setting of an honest signer, one of these branches, the pink branch, is not known. So the discrete logs are not known to the signer. But the reduction can know the discrete logs and so sign also using the pink branch. And the other property is that they are blinded in such a way that there is a hidden link between signing sessions and signatures. And this allows us to avoid these ROS style attacks. So we wanted to look into the scheme because on the one hand, it's already it's considered to be immune to the ROS attack, but the original proof for the scheme was flawed. So it was originally proved using this forking technique. And the flaw was found by Okubo and Abe, who provided a proof in the GGM. So we looked into the scheme in the AGM plus random oracle model, and we show that it is concurrently secure under discrete log. So concurrently secure means the adversary is allowed to interleave the signing sessions as well. And we also show that there's a very straightforward extension of the scheme so that we can allow also for partial blindness. That means that the signer and the user can agree on some information, and then the signature will be valid with respect to that shared information. So that's it for my talk. I thank you for your attention, and I'm happy to take your questions.
Thank you, Julia. We will take questions now. So please raise your hand or use the chat on Zoom or Zulip. So maybe I could start out the question. So for the blind signature, I do remember that for Schnorr's blind signature, there's some impossibility claiming that you can't have a security proof in the ROM. Are there some results like that for the Abe scheme, or?
So this impossibility result, I guess you're referring to this work.
Mm-hmm.
This applies to one witness blind signature schemes. And because in the Abe scheme, you have two possible branches of this OR proof, this doesn't apply there because you could, basically the idea of this is you somehow manage as a meta reduction to extract this one single witness with which you can sign. But here you have more, so in Abe scheme, you have more than one witness. So I don't think this result applies there.
So do you think, at some point you'll be able to get rid of this AGM and prove Abe's scheme in the ROM?
So I think this is quite tricky to do because if you have two, so basically if you wanted, so there's this witness indistinguishability of the OR proof, and if you rewind as a reduction, you rewind the adversary and then you redo it leaks which witness was used by the reduction. And so so there's on the one hand, you could see that there are proofs for these OR proof based schemes, but also here you have this additionally this computationally hidden link.
Mm-hmm.
So there's quite a lot of structure. So I think it's quite tricky to prove this to be secure.
I see. Okay. Are there questions right now? So if not, maybe I could ask one follow-up question. It's a bit more conceptual, but what makes AGM very useful in this setting? I don't know much about AGM, so it'll be helpful if you could shed some light into that.
Yes, so the AGM basically is a replacement for the rewinding step in this setting. So in the setting of the blind signatures, and there's more generally these kind of Schnorr style signatures where you have in the end the signature is some kind of fiat Shamir proof of knowledge of a D-log. Because the adversary needs to be algebraic, and so he needs to submit representations here when he makes a hash query. And these representations can basically be used as a replacement for the first run of the rewinding proof.
I see. Okay. We have one more minute that we can use if anybody has any questions. If not, maybe we could move on to the next talk. And if anybody has, comes up with any idea, just please ask them on the chat. Okay, thank you, Julia. Let's move on to the next talk. The title is Efficient Lattice Space Blind Signatures via Gaussian One-Time Signatures. The authors are Vadim Lubashevsky, Gokong Gwen, and Maxime Plancon. And Maxime will be giving the talk, I think.
Yep. Can you hear me?
Yep, we can.
Okay. Okay, so I should start. So yeah, so this talk is about this blind signature scheme. So first, let me start with a redundant reminder from 5 minutes ago. So in a blind signature, we have two parties, the user and the signer. And in the end of their interaction, the user should have a signature of his message under the public key of the signer. And we also want that the signer doesn't learn anything about the message he's signing. So the security is captured by two notions, which were mentioned 10 minutes ago. So the first one is blindness, which means that we don't want the signer to learn anything about the message he's signing. And the second one is one more inforgeability. So the idea is after some number L of interactions between the user and the signer, the user should not be able to produce more than L signatures. Okay, so now I give a summary of the blind signature we construct. So it's built upon three ingredients. The first one is an encryption scheme that tolerates some computations on the ciphertext, but I'll come back to that on the next slide. The second one is a one-time signature scheme. And the last one is a set membership proof, zero knowledge proof that we're going to use as a black box. I'll come back to those on the next slide. So just a quick mention that this scheme has only two rounds or two communications. So the user sends something to the signer and the signer responds, and then the user is able to have his signature. So our scheme tolerates a number 2 to the 18 signatures for the parameters we choose, and the signature is about 150 kilobytes. Okay, so now about the intuition of how we construct this blind signature. So let me just explain real quick a naive approach. So let's say that the public key is a collection of n one-time signature public keys. So in the beginning, the user will send his message to the signer. So this is definitely not blind. And the signer sends the one-time signature of his message for one of the public keys to the user. And then the blind signature is a zero knowledge proof of knowledge of the one-time signature. Okay, so now in our construction, we do some changes on the previous ID. So instead of sending his message directly, the user encrypts his message with the encryption scheme I talked about on the previous slide. So this encryption scheme allows for the signer on the next step to homomorphically compute the one-time signature from this ciphertext, which he sends to the user. And so the user can decrypt the one-time signature from the response of the signer. And then he gives a zero knowledge proof that he learned, that he knows this one-time signature for one of the public keys. Okay, now just a quick note on the parameters of our blind signature. So the public key is about 1.3 megabyte, the secret key is 75 kilobyte, the signature is 150 kilobyte, and the communications is 16 megabytes. And yeah, that's it. Thanks.
Thank you, Maxime. We have plenty of time for questions now. If anybody has any, please ask. So yes, we have one on chat. It's from Benedict. About the proof of knowledge, does it need to be straight line extractable?
Does it need to be what, sorry?
Does it need to be straight line extractable?
Straight line?
So it's one of those NIZKs where, you know, the proof of knowledge, it's not via rewinding the adversary, but you can extract directly from the proof using some simulation trapdoor.
So in this construction, we use a very specific one. I mean, for the instantiation we have, but yeah, maybe it could be, no, I don't think you could use another one just directly. And the one we use, we rewind for extracting. We can't extract directly.
So yeah, it's my question. So I was just thinking about the talk that Julia gave, and she mentioned that there may be a problem with rewinding and witness indistinguishability. So that was kind of my concern. But I don't know if you use witness indistinguishability in your one-time signature.
So I think that the problems that were discussed in the previous talk do not really apply here, because the zero knowledge proofs are done by the user and not the signer. So in the end, the signer is only going to give his response to the user, and this response is just like some computation on ciphertext. And yeah, I don't know, maybe.
Okay, yeah, thank you.
I don't think that these remarks apply to our scheme.
Okay.
Are there any other questions? So can you explain like why the communication cost is so large compared to the signature? Which part incurs this?
Yes. So the thing is, so the encryption scheme we use is a regF type encryption. And so the user sends his encryption to the signer, and then the signer will compute this one-time signature, which increases the size of the ciphertext by quite a bit, because so the message is just one polynomial, but the one-time signature is a vector. So that's the first thing. And the second one is when the signer does this computation in the ciphertext, he has to mask to add like some extra noise in the like some extra randomness, which increases by quite a lot every like all the parameters and so on. And plus we use a different modulus for the encryption. So it's like on this, like I didn't have time to explain everything, but we use a different modulus for the encryption, which is 128 bits. So yeah, the communication gets pretty big.
So I guess this is like a naive question, but even if you're using a one-time signature, and I guess you only need to kind of hide the noise once, but even then, even that will still like incur a lot of noise then. Because usually I thought like, if we want to hide the same secret for, Q times, then the noise will depend on like square root of Q, the Gaussian parameters that you have to add. But if you're using a one-time signature, I thought it will be that it wouldn't be that bad, but I guess.
So we're using so in the end we have n public keys for one-time signatures, and we're going to use them only once. So.
But even then, I guess the noise you have to add has like a significant impact in the end.
Yeah. Yes. Sure. Yeah.
And
yeah, if you want, this is one of the points discussed in the long video. If you want to.
Okay, great. So I guess we have time, so maybe I could ask one more question. So here on this slide, I guess like from what I've understood, you're using a linearly homomorphic encryption scheme, right?
Yes.
In that case, like I feel like this is a new approach to constructing blind signatures. Can it be done from classical assumptions in a secure way? I mean, like in an efficient way.
I have no idea. So,
right.
I mean, it's too complicated. I don't know. I don't want to say something. I don't know.
Okay, and no problem. No pressure. Also, I guess the final question that I do want to ask is that do you think there's a way to kind of get rid of this bounded polynomial notion? Because obviously the downside is that you need to commit to this n keys in advance. Do you think you can adaptively change this to have a more standard notion of enforceability?
So we don't need to commit to the n keys. So in the public keys is made of n one-time signature public keys. But the thing is, so instead in the usual one-time signature that we have for lattices, we first sample like the secret S and the noise Y, and then we output the public key, which is going to be like AS and AY. And here we do it the other way. We have a trapdoor in A, and we just have as the public key something that was going to generate the V's and the W's, which are AS and AY, and then we sample the secrets at each iteration. So.
Right. Yeah. What I meant is that at least like in the signing process, you need to commit to some end information, right? So you can't just make that larger.
I need to commit to.
So in the signing process, you're performing an OR proof, right, of this n public key. So you can't sign more than n, I think.
Yes. No. It only tolerates this number n of signature in total.
So do you think there's a way to get around that?
So for this construction, obviously not. We really need it, but yeah, maybe there's some other ways to. I think I read a paper by Damien Stellé that does something that doesn't require this kind of. But I don't remember enough to.
Okay. All right. Yeah. Great. Thank you, though. It was an interesting talk. So I think that uses up, that's all the time that we have now. So thank you, Maxime. So I would like to end this session by, again, like saying thank you to every speaker and everybody that participated in in this this talk, and also any future people that might be looking at the YouTube video in the future. All right, so yeah, we could stop the. No, wait, I guess we're going to the closing remark after this. So for everybody, just be here. I guess we're going to be starting the closing remark right now.
Yeah.
Yeah.
Thank you, Shu, for chairing the session. Yeah, we can start the closing remarks on time, and Junji will give out the closing remarks.
Okay. Can I see this one?
Yes, but please go for slideshow. Good. Yes, okay. Perfect.
Okay.
Oh, stop. We
okay.
cannot see the slideshow.
Oh, really?
Yeah. Okay.
Okay. So
yes.
It's just a moment. No.
Oh, we could see that, but now
we did see it briefly.
Yeah.
Okay. Okay. I see. Okay, this one.
Yes.
Okay. Okay, this is closing remarks from general chairs. I'm Junji Shikata, one of the general co-chairs. This is the statistics of PKC this year. We had 325 attendees from 41 countries, and in particular, 120 from Asia, 79 from American, and 118 from Europe. Thank you for joining this conference, and I apologize to the attendees in Europe because of time difference. Sorry for inconvenience. And we would like to thank all participants of this conference, and especially we thank to PKC Steering Committee, in particular Yurin, Moti, and Goichiro, Program Chair of PKC 2022. And we also would like to thank ISR Board and the Coronavirus Emergency Committee, in particular Michelle and Brian. And also we thank to ISR Virtual Conference Administrators, Kevin and Kay, And finally, we would like to thank local organizing committee members. We could not have this conference without their help. And also, we would like to thank many foundations, companies, and institutions for their financial support. Okay, the next PKC 2023 is not yet formally decided, but I hear that the candidate place is Atlanta in US. Okay, finally, I'd like to close this conference by saying thank you, everyone. Thank you.